Hello, everybody. Let's take a look at page 107, number 71. So page 107, number 71, I want to look at a couple word problems here. So if you don't have your textbook with you, go grab it, put this on pause and go grab it and open up to page 107, number 71. That's what we're going to start with. It says an open box, a maximum volume is to be made from a square piece of material, 24 centimeters on the side. And you can see there's a picture in your textbook, which is much better than my picture, but there's my square, all right? And basically, they're going to fold up the edges. So they're going to fold up the edges here, you know, those edges there, 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 and there, and make a box, all right? And, you know, a box, you can put things in a box, so it makes sense to talk about a volume of a box, whereas it just starts as a flat piece of paper, so it doesn't make sense to talk about the volume there. But as soon as you start folding up the sides, you're creating a box. And the thing is, and I think you may believe this or not, depending on how high those sides are that you fold up, you get different volumes. For example, you could have a box that has a really small base, but the sides are really high. That has a different volume as opposed to a box with a really big base, but the sides aren't that high. Okay. In fact, you can see in 71, part A, it says the table shows the volumes in cubic centimeters of the box for various heights X in centimeters. It says use the table to estimate the maximum volume. So if I look at that, it says if you're folding up the sides 1 inch high, you get a volume of 484 cubic inches. And again, you want to make sure you have your book open so this makes sense. If you fold up your height, your side, so you have a height of 2 inches, notice the volume jumps up to 800. If your height of the sides is 3 inches, it jumps up to 972. If your height is 4 inches, it jumps up to 1,024 cubic inches. And then it starts going back down. If it's 5 inches, your volume is only 980 cubic inches. And if it's 6 inches, your volume is only 864 cubic inches. So it seems like you make those sides that you're folding up bigger, it increases the volume to a certain point, and then your volume starts decreasing. So in part A, it says use the table to estimate the maximum volume. Well, it looks like the maximum volume is right around 4 inches. All right. And that maximum volume is about 1,024 cubic inches. In fact, if I draw that table here, just so we have reference, one was 484. 2 was 800. This is the same table in your book. 3 was 972. 4 was 1,084, 24. 5 was 980. And 6 was 864. Okay, so the left-hand side is your height, how big the sides are, and the right-hand side is your volume, which is in cubic inches. Okay, so you can see the maximum height or the maximum volume looks to be around 1,024 inches. Okay, part B says plot the points. So 1 comma 484, 2 comma 800, kind of like we did the Fahrenheit and Celsius the other day in class, or Celsius and Fahrenheit, I guess it was. From the table in part A, does the relation defined by the ordered pairs represent V as a function of X? Okay, and we're going to plot this on Desmos, which is part D also. But yeah, if V is a function of X, for every input, there's exactly one output. Remember that. So 1 goes to only one number. 2 only goes to one number. 3 only goes to one number. 4 only goes to one number. 5 only goes to one number. 6 only goes to one volume. All right. So all these heights are only associated with a different volume. It's not like you can fold it up and have 4 inches on a side and have 2 different volumes for it. You know, just logically that doesn't make sense. So yeah, this is definitely a function. And then part C says, if V is a function of X, write the function and determine its domain. Let's just go ahead and graph this on Desmos before we do part D or part C. Let me pull up Desmos. And of course, to plot this, I'm going to hit this little button here, go to table. I'm going to do 1 was 484. 2 was 800. 3 was 972. 2. 4 was 1,024. 5 was 980, and then you fold up 6 inches, you get a volume of 864. And of course, these numbers are quite large, so we probably would make sense to go ahead and change our settings on this. Our X, which is how high we're folding them up, let's just go from 0, 10 is good, let's do 1. And then our Y, which is our volume, let's go from 0. It looks like it hits a maximum right around that 1,024, so let's just do 1,100. And let's just go by 110. Okay, let's see what this does. And you can see our points there. Yep, and you can see if I do a vertical line test, passes a vertical line test. Yep, so it's definitely a function. And like I said, we're going to plot this using Desmos. We're kind of doing part D there. Okay, so we plotted the points as the relation defined by the ordered pairs represented function. V as a function of X. Yeah, for every X, there's only one V. For every input X, there's only one volume output. If V is a function of X, which it is, rate the function, determine its domain. Well, let me pull my screen back up here. Well, the volume, you know, it's a box, so it's a volume. If you look at the picture in your book, I can't really draw that well, but the volume of a box is length times width times height, okay? So here is my length. Let me get my yellow. So it's going to be 24 minus 2x. Here is my width, which is actually the same thing, 24 minus 2x, and then my height is just x, okay? And if you look at the finished box in your textbook there, it looks even better. So my volume is 24 minus 2x squared. Since I have two factors of that, you can just say it's squared times x. So that's the volume. Now the domain, you know, what you put in, these numbers here are the domain, okay? So the domain in the context of this problem is, and you have to look at it in the context, not just by looking at that equation there, that formula for the volume. This X represents how high the side is, all right? But before it's a box, when it's just a flat piece of paper, this X represents the size of this square that you're going to cut out, all right? Now, let's just think about this. If this whole side is only 24 inches, if I go 8 inches here and 8 inches here, and the whole thing is 24, 24 minus 8 is 16, minus 8 is 8, that leaves me 8 here. That works. But if I do something crazy, and if I do say, let's just cut out, 15 here, 15 here, that gives me 30 already, but the whole length of the box or the piece of paper was only 24. I can't do that. That's too much. I won't have anything left. All right. So the most I can cut off, if the whole side of the open paper, the flat paper, or the square piece of material is 24, I can only go in halfways. All right. So the domain, again, is your X. How big of squares can I cut out? Well, I can definitely cut out, you know, anything bigger than 0. 0 doesn't make sense because it'd just be that flat piece of paper again. And anything less than 12. So that is my domain, and that you have to get from the context of the problem. Don't look at that, because if I just say, give me the domain of that, that's any real number. You have to interpret it in the context of the problem. Okay, and then in part D it says, use a graphing utility to plot the points from the table in part A. With the function from part C. How closely does a function represent the data? Okay, so let's go ahead and graph this right here on Desmos, and let's just see how close this fits. So if I go and pull up my Desmos, and you know what, while I'm thinking about it, let's just go ahead and change that domain here. Let's make it, instead of 0 to 10, let's go 0 to 12, because we said that's the domain. Okay, let me plot that function. It's going to be parenthesis 24 minus 2x squared times x. And you can see, look at that. That hits it perfectly. Of course it hits it perfectly because that's the exact formula for the volume. Yeah, so it matches perfectly. Okay. And again, it doesn't make sense to start talking about these numbers down here, you know, where it gets to be negative at. Let me see if I can do that. You know, because you can't have a negative volume here. There, it's can't have a volume of 0. Okay, so if I look at this and I say when is volume maximized, the highest point is right there, and it looks like it is when you cut out squares of 4 inches, you get a volume of 1,024 cubic inches, which is exactly what it was on the table. Now that's not always the case. We knew it was going to be around 4. It doesn't always be exactly turn out exactly what may or may not be on that table. Okay, let's look at one more on page 107, same page, number 74. Okay, let's look at number 74. It talks about a rectangular package to be sent by the U.S. Postal Service can have a maximum combined length and girth, which is the perimeter of a cross section of 108 inches. So it's talking about the length would be the y here, this distance right here, and the girth would be the distance around, you know, the square. Okay, perimeter of a cross section. It says, A, write the volume of a package as a function of x, and what is the domain? Okay, so A, volume, well, this is the same shape as the number 71 was, although it's, instead of having a big base, I mean, it's a different shape, but still volume of a box, all right? So it's length times width times height. So in this case, it's x times y, okay? Or x squared y. But the thing is, though, it says write the volume of V of a package as a function of X. That means you cannot have any Y's in it. So somehow we have to substitute that Y. So if we go back to what the question originally says, a rectangular package is to be sent by the U.S. Postal Service, can have a maximum combined length and girth of 108 inches. So length and girth. So it's saying that Y is the length. The girth is a perimeter of a cross section, which if you look at this is x, 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 or 4x equals 108. Okay, that's the maximum it can be. So if I solve that for y, it's 108 minus 4x. And then you plug that in there for y, right there, and your new expression for the volume is x squared times 108 minus 4x. Okay, so volume of the box, just like it was before, but this time they said, I only want it in terms of x. So we had to use that extra information that the combined length, which is my y, and perimeter of the cross section of the girth, which is 4x, has to be less than 108, less than or equal to 108. So we used that information, plugged that in for my y, solved it for y first and plugged it in, and we got my volume. And if you notice by that, it's all in terms of x's. And it says, what is the domain of x? And this is kind of like the one that did before. In the context of the problem, you got to consider it. You know, if you just look at this equation, the domain is any real number. But in the context of this problem, remember the maximum is 108 of the girth. All right, so this x, when I add up all those sides, can't be more than 108. So if I do 108 divided by 4, and you run that through, or just do it in your head, 108 divided by 4 is 27. So this can be no more than 27, okay? So if it's more than 27, you know, if it's 27 exactly, 27 and 27 and 27 and 27 make the 108. all right, that means there's no y, because that's the biggest it can be. So it has to be less than 27. So the domain, of course, it's positive because it's a distance, but it has to be less than 27. It says use a graphing utility in part B. So we got the volume of a function of x, the domain. Use a graphing utility in part B to graph the function. Make sure to use an appropriate viewing window. So that means make sure you see the picture. So I'm just going to pull up Desmos again. Let me just X this out, X that out, and notice you can type in y equals, or you can just type in x squared, and then 108 minus 4x. And you can see here, let me just zoom out on it a little bit. And you can see here, you know, it's kind of that same shape here, okay? Let me go to my wrench. And we said that it's anywhere the domain was from 0 to, I think we said it was 27. There, that looks better. That looks better. Yep, so that's the domain. That looks like a good viewing window. An appropriate viewing window would be the one that has a domain in it. And then notice I can see the maximum value right there. I can go up there and see what that maximum value is, which is part C. It says, what dimensions will maximize the volume of the package? Explain. Well, the maximum volume here would be at this high point, also known as a maximum. If I just click on that, and looks like it's 18, 11,664. Okay, let me pull my whiteboard back up. Now, 18 was my x. Okay, so it's saying that if all these sides here are 18, 18, the dimensions, so the square is 18 by 18, but how long is it? If I plug in 18 right here for x, and you saw that, so if you do 108 minus 4 times 18, you get a length of 36. Okay, so the dimensions of this box are 18 by 18 by 36. Okay, so the dimensions would be 18, and I believe it was inches, by 18 inches by 36 inches. And that will maximize the volume of the box, all right, and still be within the constraints of having a maximum girth of 108 inches, okay? And again, we just graphed it. There are other ways to find this maximum value. We're not there yet. We just graphed it, all right? And then clearly that's the highest point in that area, so that's why it's called a maximum. You know, if we would do this problem, we'd want the lowest point. You know, if we're trying to minimize cost, maybe we want to do a lowest point, that would be the minimum and not a maximum. Let me make sure that there's nothing on the next page, and there's not. So it looks like we did everything on number 74. Find the volume of the package as a function of x. Again, we had to use, you know, this was our original volume, x squared y. There it is, x squared y, but then use the information of the constraints of the girth. We were able to solve for y and put it all in terms of x. So all in terms of x means there's only x's there. Okay, we found a domain based on that constraint of 108 inches for the girth. We graphed it using that domain from 0 to 27, and notice what happens when we graph it after 27. You know, it starts dropping and having a negative volume, and you can't have a negative volume. That doesn't make sense, all right? You can't go over on this side here because that would mean your x values or the size of the, you know, that box at the end, the square of the end would be negative. That doesn't make sense either. And then we found where it's maximized right at that point, 18, 11,664. So 18 inches. So when x is 18 inches, we found the dimensions were 18 by 18 by 36. All inches, that 11,664 would represent the volume, and that would be in cubic inches. All right, thank you very much. I hope this helps out when you're doing your homework for section 1.3. Thank you. And please email me if you have any questions.